2.2 is going to be considered the derivative at a what? Derivative at a point, okay? And so what we're looking at today, guys, is this. We've talked about this phrase right here. How is instantaneous rate of change related to what?
Finding the derivative at a point and what does it represent?
Okay, so we know kind of from what John asked about in number 8 on the previous section right here that an instantaneous rate of change is basically, what kind of a line is this to that point? It's a tangent line. It's really the slope of a tangent at that point. So we're saying the instantaneous rate of change is really the slope of a tangent line at a point. And we're going to start looking at that, what that represents today. So in order to understand our question or answer this question, we're going to look at finding derivatives at a point. How? Graphically. And we're probably going to use what for that?
Decimals.
Yeah, because we like decimals, right?
Yeah.
I tell you what, I wish decimals was around in, like, say, 1990. Oh my gosh, did I just say that?
Oh my gosh.
1990, I was in high school. So decimals graphically. Secondly, then, we're going to look at derivatives at a point numerically. You've kind of done that. What values were we putting in number 21 for Maddie's question today? Okay. Are we looking at slopes over great big intervals or very, very small intervals when we want to get that slope of a tangent line?
Small.
So if you can kind of think everything we're going to do is going to occur over a very small interval, I think that'll help you numerically. And then we're also going to use the idea of a derivative at a point algebraically today. And this is going to be a big idea today. This is going to be a focal point, so you might want to put a star by this because the next section, it's all about general derivatives. Not specifically a derivative at a point, but a rate of change anywhere on a graph. Okay? So, vocab-wise, we're kind of in the same situation. Have we talked about average rate of change? Absolutely. Last section we said the average rate of change of f on the interval a to a plus h is f of minus all over what? Okay. And we'll look at examples here in a little bit. But this is the part right here where we start talking about the derivative of f at a. Now, if you remember on the quick quiz or one of the examples, you start seeing f prime of a like this. What's this mean, kids? The derivative of some function f at a point a is written as f prime of a. And really, guys, all this is just saying, what's the slope at a? Okay? Now, this is the general definition for finding the slope at a point a. F prime of a is approximately the limit as h approaches what? 0, because we're looking at slopes over a great big interval or a very, very small interval. So that's why we say h approaches zeros of f of a plus h minus f of a all over h. Okay? Guys, there's going to be some stuff that comes up in your questions. Is this differentiable at a? Okay, is the function differentiable at a? When I ask you this question, they're simply asking this. Is there a limit or is there not a limit? Okay? It says if a limit exists, then what? Okay, so there's a slope there. If there is no limit, like say, remember when we had an asymptote there? Maybe the right side goes to positive infinity and the left side goes to negative infinity. What's the slope there? We're like, well, I don't know. It's positive on the right of it and negative on the left. Okay, so it's not the same either way. So the limit has to exist for something to have or be differentiable at a. Okay, let's get rolling. Example 1's a good one. It says visualizing the definition of what, kids? Okay. Let's write that definition of the derivative down again. It's the limit as what? It's the limit as h approaches. It's right up there in your vocab. 0 of what?
Oh.
Okay. Should we visualize this puppy? What the heck does that even mean? Okay, here it is. Let's just say I have a point, so make an XY axis. How's that sound? Let's make the first quadrant kind of like this. Okay? You guys cool with that?
Is that supposed to be h or an f of h?
Oh, this is an A. Appreciate it. You caught me. It's the first mistake I've made all month. All right, I guess it wasn't funny. Should be F of my right there. Maddie, thank you. You okay with that? What did you say, John?
So what is the derivative then?
I'm working on it right now.
Okay.
Okay? All right, so let's make a sketch of the derivative of f at what, kids? All right. Just pretend there's some graph up here. I don't care what the graph is. Okay? Now, kids, you need to understand that this is a very small interval that we're talking about. Okay? It's just like on the graph over there that we did with decimals. We just kept zooming in and zooming in and zooming in. Even though it gave us a graph, was the window a really big interval that we were talking about or a very small one? We keep zooming. It's very small. So here's the deal. This point right up here happens at maybe when x is equal to a. All right? So maybe this point right up here is f of a right here. That point is f of a. Okay? Now, guys, if you have some value a and you add a value h to it, is that going to be more than a or less than a? And we assume h is positive. It's going to be more than that. So we'll say maybe a plus h is over here. Okay? It's over there. Now again, that distance from a to a plus h, really big or really small? It's very, very small. It's infinitely close to what? It's approaching 0. Okay? Well, guys, if this point up here is f of a, what's this point up here? Okay, so here's what we start running into. You're going to get asked this a lot, and this is the best visual I can give you of this thing, kids. They're going to say, okay, well, what's the distance from here to here, kids? It's h, right? That distance right there is h, all right? Because a plus h, if this was 7 and this was 3, you would take 7 minus 3, wouldn't you? To say it's 4. But this is a plus h minus a. What do the a's do to each other? Okay. How about value-wise? This value is f of a. This is the value f of a plus h. How about this distance right here then, kids? Well, if this was 12 and this was 3 down here, you would take 12 minus 3, wouldn't you? To know that that's 9. But what is this? F of a plus h. What's this? Okay, so if I say the whole distance, this is f of a plus h right here, take out f of a, wouldn't this part right here really represent f of a plus h minus the distance f of a? Because again, if this is up here 12 units and this is up here 3, as an example, if this is 3 units from the total 12 would make the distance in blue how much? Well, 9, right? Okay? Now guys, I'm not gonna lie to you. F of a plus h minus f of a. Is that like a rise or a run? Or a change in y values, right? This is like your rise. What's h like, kids? Okay. Run, boss, run. You know what Forrest's password is, don't you? You know what Forrest Gump's password is?
So then that limit is the slope.
Yeah. You know what Forrest Gump's password is? You don't know Forrest Gump's password?
No.
1 Forrest 1. Okay, never mind.
Or it's capital
What's the matter with you guys today? What?
capital J 3 N N Y.
Jenny? All right. Like, you said something interesting. Say that again.
Isn't that limit just the slope?
Yeah. Because a rise over my run between the 2 points is the slope, isn't it right here, kids? Wouldn't that be the slope then between the two?
Yes.
Wouldn't that be this over h?
Oh, it's like
Or this definition right here, isn't this definition right here really just your what? This is just a fancy way of saying what, kids?
Whoa.
Okay, that's how you visualize that. Okay. Now I'm not gonna lie to you, that drawing, that's pretty important, so I make sure you have everything down, because they're gonna say, what's f of 3 minus f of 2? Where is it? Well, that's like the rise, and you have to represent that in graphs. So we'll look at that when we do the problems, okay? There's a lot going on here. This, guys, this is just a fancy way of saying this is a slope for a very small interval. Okay? So let's see if we can't apply some of this stuff here. This is just a fancy way of saying, oh, that's the slope for a very small interval. And a very small interval is really close to the slope at a point A. All right? So let's take a gander at this. Calculating average rates of change. You know how to do this, okay? This here says calculate the average rate of change for the volume V of a what? Sphere with respect to the radius what?
R.
Okay, well, over what interval? 1 to 2, okay? Let's just assume that R is measured in centimeters. Is that okay with you guys? R is measured in centimeters, okay? So if we're going to go ahead and talk about the volume of a sphere, kids, we better know the volume formula of a sphere. So we're going to write a volume formula with respect to the radius. Anybody recall the volume formula of a sphere?
3/4.
I hear 4/3. I like that. Close, so close. It's a volume, so it'd be cubic units, right? All right, there's your volume formula for a sphere. Now, we want to know what's the average rate of change, and when we talk volume, what kind of unit is volume going to measure in if the radius is in centimeters? Cubic centimeters, right? So what we would need to know here, guys, to understand the average rate of change, if you ever see me write this right here, simply means what? Okay, we would need to know the volume when the radius is 1 centimeter and the volume when the radius is what?
2.
Okay, I need a volunteer to help me. I need somebody to figure out the volume when the radius is 1. So somebody's going to plug 1 in for my radius here. And then I need someone to plug in 2 for the radius. Who's willing to plug 1 in for the radius and solve that for me? 4/3 pi. So give me a decimal on that. Let's just go maybe 2 places. So .188. So about 4.19 cubic centimeters. Okay. How about the volume when the radius is 2? Eight and 4 is 32. 32 over 3. Take 32 times pi and divide it by 3. How much?
Yeah.
32.51? 33.51. Is that what you had, John?
Yeah.
Okay. And I should put cubic centimeters up here was the volume. All right, guys. What they're saying is this. They're saying between the change from the radius going up 1 centimeter to 2 centimeters, what was the average rate of change of volume? Okay. Well, that can simply be found by taking the volume at 2 centimeters minus the volume at 1 centimeter. Wouldn't that be the change in volume? Or the change in radius. So it's pretty straightforward. The volume is going to change by 33.19 minus, 51, I'm sorry. 33.51 cubic centimeters minus and then this is all going to be over
what's the interval from what to what? So that'd be 2 minus 1, right? Whoops. Okay, I don't know what that is up top. Help me out, kids. 29.32, is that right? Okay. Okay, so what that means is this. The volume change is 29. On average, the volume change is 29.32 centimeters for every 1 unit of change in my radius. Okay? Means the volume changes, adds 29.32 centimeters, cubic centimeters on average for every
Why don't
one.
you take away the CM?
You could, you don't necessarily have to. I'd be very careful on that because you're not adding area really. What you're really adding is you're adding a certain number of cubic centimeters to that sphere for every 1 centimeter change in the radius, okay? So, you know, you guys have done average rates of change, right? Now guys, would this interval probably be considered a big interval or a really, really tiny interval? It'd be kind of big because we want to look at stuff like to the nearest 10th, nearest 100th, nearest 1000th, maybe even nearest 10,000, okay? So let's get this idea of instantaneous rate of change at a point. I'm going to be honest with you. Kids, if you can understand example number 3, if you can understand example 3, I think you're going to be in great shape. And again, there's a lot of tie-ins to the last section. So it says from example 2, estimate the instantaneous rate of change of the volume when the radius is what? Okay, go back to your vocab and take a look at your vocab for derivative of f at a point A. It's basically the slope, I think, right? Now, did I put a formula over there for derivative at a point A? Here's what we're going to do, kids. Here's what we're going to do. We're really looking for the derivative of what? With respect to when r is what? What we're really looking for, kids, is this. We're looking for the derivative, how quickly something is changing. We're looking for the derivative of V at what radius specifically, kids? At 2 centimeters. Okay, how quickly is that volume changing when the radius of my balloon is 2 centimeters? Okay. Well, here's what we're going to do. You're going to have me writing this down a million times because you're going to have this so memorized in your head. The derivative at a point A is the limit as h approaches what, kids? 0 of f of, in this case, what is our A value? What point are we at? We're going to be f of 2 plus h minus f of what?
2.
All over. Oh! Okay. Well, here's how you handle this. We want h to approach what value here? So here's what we're going to do. Let's come over here and say let h equal. Okay, when I tell kids to pick a value for h really close to 0, that's what I typically tell them to pick. Pick 0.0001. Okay, 3 zeros and then a 1. It's really 1/10,000, isn't it? Okay, so here's what we're going to do, kids. I have a question. This then becomes the limit as h approaches. I screw this up all the time. All right, how about this 2 plus h part? What is 2 plus h going to equal? Okay, and so I should really put a v up here, the volume of 2.001. minus V of what?
2.
All over the H value, which we chose to be what? How many cubic centimeters is basically being added to that balloon when the radius is at exactly 2 centimeters? That's what we're after right now. Okay? And here's the deal. Guys, from the previous example, did we know what V of 2 was equal to already? What was it? 33 point what? 5.1. So what I really need someone to evaluate is not V of 1, not V of 2, but V of what? Okay, who wants to put in 2.001 to the third times 4 pi divide 3 for me? And give me that exactly as it shows up, all right?
You want us to use 2.001 or 2.0?
Did I put, yeah, it should be 3 0, shouldn't it? And that's a common mistake. You'll make, you want to know the nice thing about this, though? We start getting down that far, we're usually pretty close. So I'm going to go 2.001 to the third, right? Times 4 pi divided by 3. What are you guys getting? What did you guys get here? You get 33.5606. Okay, so I'm going to write this whole thing out. This volume of 2.0001 into my formula. What value are you getting? I'll try and squeeze it in up here. Is it okay if I call it about 33.56? Is that okay? How about 33.5? And I'm going to write, do you guys have 6061226? Okay, all I did was put 2.00. Hang on a second. Maybe I have something different. Hang on. That's the radius times 4 pi. I have 33.5153. Okay, read that to me. 31 point. Okay. I'm going to move that value. I don't like that there. So 33.515. 34844. Okay, we're going to subtract V of 2. What was V of 2, kids? Up in the previous example. 33.51. We're going to divide this whole answer by what? Okay, and keep in mind, all we're doing is looking at a slope over a really big interval or a really small interval. Really big interval or really small interval? Okay, so I subtracted 33.51 and now I'm dividing by 0.0001. And I have, what do you guys get? 53.48. So guys, what's happening here when I do this here is this. First of all, this is kind of saying that when the radius of that balloon becomes 2 centimeters, when the radius of that balloon growing up like this gets to 2 centimeters, it's adding about how many cubic centimeters to its volume at a radius of 2 centimeters. Yep. So we're adding about 53.48 cubic centimeters in volume when my radius is equal to what? To what? Okay. So instantaneously, this is saying when that radius is equal to 2, there are exactly 53.48 cubic centimeters going into that balloon at that point. At that particular point, the rate of change is 53.48 cubic centimeters when R is exactly what value? 2. Okay? Now again, I'm going to keep telling you, everything in this section is to look at a derivative over a very, 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 very what? Small interval. So let's go ahead and look at example 4. Again, this is nothing more than a fancy formula for finding what? Slope. So we'll use decimals to visualize this next one. Okay? It says, is the derivative of cosine of x at what point, kids? Positive or what? Negative. And then it says approximately what is the derivative of cosine of x at what? Okay, so let's take a look at this. Let's get into decimals. First of all, if you ever have any trig functions, make sure you're in what mode? Make sure you're in radians. Let me zoom home. I've done that. All right, kids. What's the function again? Cosine of x? Okay. Guys, question for you. Pi over 2 is right there, isn't it? Is the derivative at pi over 2 positive or negative?
Negative.
Okay, anytime you hear me say the word derivative, you're looking at the
Slope.
slope. It's negative. We can see right here that the slope is negative. Okay. I'm going to go in here and type Harson, and you're like, I think the slope is what?
Negative.
Negative, because the graph at pi over 2, increasing or decreasing? By the way, is this graph differentiable at pi over 2? Does the limit exist at pi over 2? In other words,
Yes.
to the left of pi over 2 and to the right of pi over 2, is there a pinching point?
No.
Absolutely. Plus it's continuous there. All right, this graph continuous. Check it out. We're going to say derivative is what? So now approximately what is the derivative? All right. Guys, if I want the derivative rate at a point, can I look at the window I'm in, or should I probably zoom in on it? All right, let's zoom in on it. Let's, I don't know. How far? I want to keep zooming until it looks kind of like a straight line, don't you think? Are we getting close to a straight line? Okay, now kids. At pi over 2, what's the y value? Okay, so here's what I'd probably do. Figure out what pi over 2 is as a decimal. 1.57. Okay, should we pick a point pretty close to that? How about, let me get something, I don't know. I have a better idea. You want it? How about I type in Is this okay to use with you guys, 1.576? Come on. How about 1.577? Look at my points there. Have you got them? Gosh darn it. How about I do this? Let me do this. I'll type in x equal, I had 1.577 there, and I'll get you a value right there. Do you guys have those 2 points written down, 1.57 comma 0 and 1.577 comma negative, what is that? 0.0062, is that right?
What's the first one?
So the first one was pi over 2 comma 0 up here, right? So you want me to pi over 2 is approximately, we'll go one more place on that pi over 2. Pi divided by 2 is 1.57, it's actually 1.571. You okay with that? Okay, so here's what we're doing. We're just looking for the slope between 2 points there at pi over 2. And here's what I would tell you. Your point, so what was that second point, kids? 1.577 comma what? Negative point, was it 2 zeros or 3 zeros there, Maddie? 2? 0062? And then we said the other one was 1.571 about, comma 0, right? Because that was the point, pi over 2 comma 0. So if we want to know the slope at that pi over 2, which is that 1.571, don't I have 2 points that are really, really close to each other? Won't that give us an idea of what the slope is right around there? Okay, let's do the math. Negative 0.0062 minus the 0 for change in y. So I would write this down. Here's how I'm going to write this down. In this case right here, slope at x equal pi over 2 is approximately equal to negative 0.0062 minus 0 all over what? Well, isn't that 1.577 minus 1.571, where 1.571 came from what? Where did the 1.571 come from? Pi over 2. Okay, so this is about negative 0.0062. Whoa, gosh. What's going on here? All over, is this 0.006, is that right, guys? Anybody want to divide that out for me? Tell me what you're really close to. So negative 1.03-ish, okay? What if I told you that the slope there is actually negative 1? Probably pretty close. Negative 1.03. Pretty close, aren't we? Okay, so slope at x equal pi over 2. Is, what'd you say again? Perfect. I love it. Okay. If I ask you to visualize something graphically, what are you going to keep doing? Zooming in. Okay, window really big or really small? The idea here is still you have to find the slope. By the way, did what we see visually match what we thought algebraically or mathematically? Derivative is negative. Did we get a negative value? Okay. So it's, because that's pi divided by 2, John. Okay. That point, pi divided by 2 comma 0 was a point. So to make sure we could find the slopes, I turned pi over 2 into 1.571. All right. So what's going on here next page? Ooh. You guys are going to tell me how to set this up. I want to know the slope of the function f of x equals 3 to the what? 3 to the what? At what point? Okay. Let's do this. What do you want x to equal?
1.
X is 1. So how about our h value? What did we say we should probably make it? 0.00. Okay, watch this. So we'll do the numerically part, and then we'll confirm this graphically when we get to class tomorrow. Numerically, kids, here we go. This becomes 3 to the, all right, what's 1 plus h going to be when I plug it in? Wouldn't that be to the a plus h right there? The 1 plus the h? Minus f of a, which is just going to be 3 to what power, kids?
1.
All over what value? Ooh, careful. We got h down here. Remember by definition h divided by what? I would almost offer this, kids. In your calculator, if you can go 3 to the 1.0001 minus 3 to the first. 3 to the first is going to be what value, kids? And then divide that answer by what? What are you guys getting for that? Ooh, I don't like that. Okay, so I'm going to go 3 to the what power first, kids, up there? 3 to the 1.001 minus. And then divide by 0.0001. I'm getting 3.296, which is going to be right around 3 point what? 3. So the slope for the function, 3 to the x, when x is equal to 1, is about how much? Okay, slope is about 3.3. And we'll look at that tomorrow and see if that looks about right. All right, have a good day.